This is Adam Green here from ATA Engineering, and welcome to our webinar this afternoon, Engineering Simulation for the Nuclear Power Industry. And we are joined by some folks from Siemens, Brian Haley, Sean Bagley, and Brian Thornton. They're going to talk to us about basically some industry trends, various kind of specialties of the Siemens software and application, and also some model-based systems engineering. So welcome everybody, and we look forward to hearing what you've got to say. So basically, I'm just going to do 2 minutes on who are ATA. And so ATA Engineering are an engineering consulting group, basically who specialize in kind of advanced problems. We have 200 staff, over 170 of them are degreed engineers. And really the key thing to see from this is on the left, the number of skilled people we have at really high levels. And secondly, the average years of experience, over 15 years across the board. So you can see that we have a lot of depth in our skill set for really using both simulation and test and various other applications. And so when you look at the industries that we work in, often we're doing aerospace and spacecraft and defense as our most common industries, but we also work in a lot of power generation, some themed entertainment, and more recently some hypersonics and composites. And we work in various capacities in all of these industries, from basically analysis to test to structures, all kinds of things. And so when you look at our core disciplines, we do design from really initial concept all the way through to structural design. We do complete analysis using really all the tools that we're probably familiar with on this call, from CFD to FEA to really every tool that Siemens mostly offers. And then we also do a lot of tests. We're very big into test, and our history, in fact, for those of you who've been in the industry long enough, ATA originally started out as a test group within SDRC, who were the original creators of unit graphics and ideas. So you can see our legacy goes back a long time in test and in 3D CAD and CAD CAE. And we have offices across the country. You can see the map there on the West Coast and in some central cities, and also Huntsville and DC. So really mostly the aerospace centers of the US. And when you look at those application areas, design, analysis, and test, we also use Siemens tools in great detail for really every part of those tasks. And because of that, we've built up years of expertise in really all the Simcenter tools, and more recently in Simcenter test as well, for conducting our work. And a lot of our support people are also doing services work and consulting all the time to really hone their skills and keep them at the top of their game. And so when you look at what we provide of our clients, we provide full support for Siemens services. We're a platinum level solutions partner, which means that's the highest level there is, and we sell software in pretty much all of the Simcenter portfolio and some others. We have dedicated hotline support, and really it's our support and our attention to customers that really makes ATA one of the most successful Siemens partners, because of the depth of our skills using the tools every day. We can really connect with customers and help them solve their own problems. And we also do software implementation if you need to connect software from Siemens to other things, from MATLAB or really anything you might think of. We're experts at that, and we also have our own tools to make that easier, called ATA Suite. Going back to the connection with SDRC, because of our length of connection with Nashtran, we are the main provider of training and training materials for Nashtran for Siemens, and we're also a Siemens preferred provider. So you can see that we are a very skilled bunch of folk, and we have a lot of connections to Siemens and the Simcenter portfolio. And so a lot of places, a lot of areas where you can find all of the details and much more about this is on our website. If you go to ata.com/software, you can see all of this, and you can connect to a lot of resources for that. And to that end, this webinar is being recorded and will be put up on the website and available on YouTube later. So if you want to revisit some of the details that the folks at Siemens have talked about, you can do that there. And so with that, I am going to ask Brian Haley to step up and take the ball from me and start talking about Siemens and the overall position in the nuclear power industry.
Sure.
Brian?
Okay. Thanks, Adam. Okay, so just a quick introduction. My name is Brian Haley. I'm an Siemens Industry Partner Sales Executive based in Houston, Texas. And I wanted to get started today talking about some industry trends. I think we're all pretty familiar with them within the energy and utilities space, which is what I cover. Obviously, there's a big focus on reduced emissions to the tune of 50% decrease in this decade and to reach net zero by 2050. So to do that, we're going to have to focus on increasing renewables, electrifying mobility. Carbon capture is huge, but mostly what we're going to be focusing on is finding net zero alternatives in the form of new types of energy, nuclear being one of those. So at Siemens, we go to market using digital threads. So what is a digital thread? Well, just think of it this way. It's a connected flow of data that enables digitization and traceability throughout a product's lifespan. So for today, we're going to focus on the digital thread of advanced engineering simulation and how our simulation tools can help streamline your design and your operational process through digitization. Sean and Brian are coming up after me, and that's going to be the main event for today for sure. They're going to be shedding some light on STAR CCM and how our solutions can provide simulation capability over a wide range of design processes, including systems design, fuel design, and even down to reactor reliability and economics regarding the nuclear power industry. So another thing that I wanted to point out before Sean gets started, and this is something that he's probably going to touch on quite a bit, is the fact that STAR CCM and our Simcenter tools offer NQA1. That is a huge, unique differentiator for us in this industry because of the safety assurances that nuclear customers require. At this point, I'm going to stop talking and I'm going to turn it over to Sean Baggerly. So Sean, take it away.
So I come from a very long energy background. I've been with Siemens since 2002 on and off. I've done everything. I designed one of the largest and I helped design one of the largest and fastest coal conveyors in the world at one time. I've worked on designing some of the larger pipelines in the world. I've done a lot of power generation work. I've done a lot of work with utilities. So I come from a long history of dealing with this subject matter. And I took over the energy interests of Siemens software about a year and a half ago. I actually came out of a large inverter organization where we were designing pipelines and things during the shale boom. And initially I didn't have nuclear as a responsibility. And about a year ago, they gave it to me, and I'm glad they did, because I am actually really interested in it, and I'm fascinated by both the simplicity and the complexity, especially from a materials and performance standpoint. And when I really got into looking at nuclear versus the alternatives, when they finally told me my beloved oil and gas was going to be put to pasture, I've become convinced that any responsible future energy policy is going to have to include nuclear power. One interesting stat I read that is on a footprint roughly half the size, a nuclear power plant can produce roughly 10 times more power than a solar field. So it makes sense. Now, it's not without its challenges, obviously. It is a highly regulated business for obvious reasons. And we do have increasing competition coming from solar and wind and things like that are driving the cost per kilowatt hour down, especially with the subsidies they receive from the government. And from a CapEx standpoint, especially in terms of a large nuclear power plant, and from a timeline standpoint, it was really hard to get those things approved and built within the same amount of time we could do an equivalent power solar field in spite of the smaller footprint. Also, there's the public perception issues, things like that. So I was really excited to see these emerging technologies, these modular reactor designs. I got involved initially with like NuScale and got familiarized with that. And then as I started to really branch out and get to know people in the space, I've seen some really, really cool, really interesting, really innovative reactor designs. And obviously, when you're coming up with something new that's dealing with nuclear power, you're going to have to go through some hoops, and those hoops aren't going to be cheap, and they're not going to be fast. So what you're looking for is ways to increase the competitive nature of what you're trying to do. Some of the ways you can do that are like, designing things that don't require new materials, designing these reactors to made up to kind of like as off the shelf an existing steam turbine system as possible, for example, or hydrogen generation. I've even seen some things going on with that now, specifically in the area of chemical plants. But basically, I mean, all the nuclear plants have basically the same challenges. You're looking for some kind of fuel performance estimation, thermal, burnout, like plant performance. How can you produce the most kilowatt hours or megawatt hours per year based on your reactor design? And then, as I mentioned earlier, the advanced reactors. Then beyond that, we have back end. What do you do with the spent fuel? Where does it go? How do you handle it? I've seen reactor designs that are cycling fuel continuously back through the reactor until it reaches its burnout, and then it's disposed of. So I've seen a lot of interesting things. But basically, what you want to look at is to utilize these simulation tools as much as possible from the beginning. And I'll tell you, when you start modeling your thermal, your flow, and your neutronics using these tools, you'll find that the simulation allows for far better understanding of your design margins. And that goes directly to optimizing your cost without compromising the safety of the system. So it's become a really, really important tool. And a lot of the stuff I've done in my career when I was working on it, we didn't have stuff like this. I can tell you some horror stories, things I helped design and then wound up having to tear equipment out, refit it. Sometimes I had the wrong stuff in there completely. So I understand the problems that arise when you lack planning. And so these tools have, in my opinion, really revolutionized the way that you design things. And at the end of the day, what's interesting about them is, although they're simulations, they're still basically, for all intents and purposes, objects in terms of how they live in a computer, right? So you still have to do things like manage revisions, connect things, and then they get really complex too. That one piece of design may relate to something else, 2 simulations over. How do you know what you change on one of these is going to impact other parts of your design? So the tools to tie those things together are really powerful, and they couldn't have come along at a better time. In fact, they're what's making some of this possible. So what's kind of the process you go through? Well, the first thing you want to do is build your models, right? Then you want to take something and, like we say, explore the possibilities. Now, there's a lot of ways you can do that, but there's some mathematical tools out there in the context of machine learning and things like that. Specifically, you can really get to better designs quicker. And not only that, once you've done that and you understand what the margins are, you can actually end up with a situation where you find that you can actually get to market a lot faster. And then you can keep all that information, the workflows, the content tied together, so that changes that affect one thing, you can let someone know who may be working on a different part of the process. And you can collaborate in these tools and come up with updated designs in a much more efficient way and with more integrated communication capabilities. So our tools that allow us to create these simulations kind of in a virtual environment and holistically is called Simcenters. That's the brand. And Simcenter includes a lot of things. So we've got 1D simulations. We've got Flowmaster, which is something I'm using right now, a lot of in the pipeline space. We've got AimSim. We're using that to simulate things like battery performance when they're put into a pack. Then we've got in the next slide, or the next row down is kind of our 3D simulation suite. You got Star CCM, which Adam mentioned earlier and Brian mentioned. We've got Simcenter 3D, which is we have NQA1 on that. I think it just was released a couple of months ago, so we do have it on our 3D design environment now. We have, as Adam mentioned, Nastran, FEMAP, these tools that have been around a while and are fairly popular in different things, not probably so much in the nuclear space, but they are part of our suite. And then you have the physical testing suite, and that's some stuff I've been doing lately in the semi space as we start bringing chips back to the US. That's becoming kind of a hot topic. But what I want to direct your attention to is this area over here. I think this is a really good representation of how you can actually design these simulations, and then you can use things like the machine learning. Now, we call it exploration, and I'm going to demonstrate to you in a minute kind of what this is. And then you can tie all the communication, the process, and the content together using Teamcenter and Teamcenter simulation. So to simplify this a little bit, basically for your fluids, your thermal, your heat transfer, that's going to be done primarily in what's called Star CCM, which is right here. And then you have your structural, your fluid structure interaction, things like that. That's more like a Simcenter 3D type conversation. And then your Flowmaster would be just modeling flows and things like that. So when you take all those things, you may have multi-disciplines involved in the design, and you will. So how do you take those disciplines and then kind of wrap around a mathematical tool that will give you, help you optimize those answers? And we call that HEEDS. So in the advanced reactor space specifically, you have quite a few challenges, and I'm going to speak very generically because every one of these reactors is a different design. Some of these guys are using helium as a heat transfer medium. I've seen a lot of molten salts, and some of the things that arise from that, right, are like you want to take your flow calculations, you want to minimize pressure drops because that increases the overall power output. It improves the economics of the plant over time in terms of power generation asset. You want to be able to optimize safety. You want to do as much as you can to have passive safety mechanisms that don't require power, so we don't end up in a situation like Fukushima or Chernobyl. You want to make the most economical design possible by using existing materials. You want to be creating new materials all the time to try and handle some heat or some exposure to some surface or radiation that you can't handle with current materials. And you want those to be as low cost as possible. So when you start looking at like really optimizing these reactors, you want to minimize your power density as well, so that you don't end up with a situation where you get a runaway thermal event and you get a meltdown. So all these things come into play, and then you're trying to also model the cooling medium and the heat transfer into things like steam turbine generators or whatever you're looking to do. So, and then the fuel management's a whole nother conversation, and it's really interesting. These pebble bed reactors are pretty cool. I've spent a lot of time with some of the guys that are using those, and the cooling medium stuff's cool too. I spent a lot of time talking to some guys in California just about the graphite blocks they put in their core. Another good example of where Star CCM can be utilized is to model under heat and high radiation the shrinkage of those blocks in time. What I thought was really interesting about that is that, of course, when the blocks change shape, you need to know that for a lot of reasons. But in the case of like a molten salt reactor, those blocks actually become buoyant and float. So they had to put a special design in there so they would interlock. I thought that was really interesting. So in the advanced reactor design, this stuff is I think it's a design imperative now. Just to get your cost right and to get the economics of the plant right, to get your safety right, and then to get this to a point where it is something that's kind of acceptable by the public, because this passive safety mechanism, to the degree possible, I think is really an important feature. So I'm going to give you guys just an example. Now, this is more from like a typical nuclear rod spacer example, but this is a good example where star CCM has been utilized. These rods are coated in zirconium and they have uranium fuel pellets inside of them. And what they found was over time, these spacers here, due to turbulence in the flow of the coolant around these rods, was causing wear in the zirconium. So the task was to basically change the shape or the distribution of the way these rods fit together in such a way that it would eliminate some of that turbulence and therefore some of the vibration and movement inside of those grids that was causing that wear. So to do that, they created these models in STAR, and they actually linked it to that tool I mentioned earlier called HEADS. And what HEADS does, now this is an example from the semiconductor world, this is not a nuclear plant, but you give it some boundary conditions and it's going to iterate through every individual design it can come up with. This may take thousands, it may take millions of iterations to get what you want, but it will give you the actual plots and the data, and it will actually help you optimize what you're trying to accomplish. So I'm using this right now in pipelines. We use it in chemical reactors. It's being utilized all over the place. And I was really astonished at how easy this thing is to use. Whenever I started playing with it, I took a couple of years of machine learning at University of Texas a few years ago, and I used Python to come up with some of these solutions, not for problems necessarily identical to this, but similar. And this is a drag and drop staging. I mean, you can actually tie your model to a spreadsheet, to cells from a website. I mean, you can bring almost anything in, and HEADS will optimize it for you. So when you're talking about trying to optimize those economics and things like that, this is a good way to take a look at all the different possibilities. It will run these simulations for you, and it will give you a report that tells you what the optimal is. And I don't have an example of that here, but I wanted to really highlight the interface to this tool because it's the easiest I've found in terms of optimization, and it's extremely powerful. So once you've got your models, you've got your optimized models. I'm seeing a lot of people in the nuclear space start to have these conversations about what's called a digital twin. Now, what is a digital twin? Well, in my mind, a digital twin means that you have a lot of models, you have some operation that you're trying to mimic, and you need to assess the complexity of the model so that you can scale the mathematical complexity accordingly, such that that model could be run in real time next to the process. Now, we happen to have a tool that allows you to do that. So when you reduce, it's called a reduced order model builder. And what you do is you take your high fidelity models, you would utilize this ROM tool. It's going to give you, some information. You're going to run your validation, your test data. It's going to tell you you're 98% based on the model it currently has. So then it's going to run it without one variable. It's going to run it without two variables. And it's going to go back and it's going to back calculate and figure out what percent accuracy you can live with while minimizing the computational load. So when you start really thinking about how to do this, this is the next step in that process for those of you that are kind of on the path and have groups internally to start working toward this digital twin. So these are just some of the mathematical tools that are used to create those ROM builders. You see you have information from the process itself. Usually we're doing a lot of this in battery right now. You have simulation process. It's going to figure out what it needs to get to the level of accuracy that you need. And then it's going to basically present that to you in real time. What that allows you to do is a lot of things. One of the most important things is to do engineering studies and things like that in a much more efficient way. And you can also tell whenever there's an operational outlier without having to do a complex study. So these things are becoming more and more popular. We're starting to see it a lot. And this is basically the path you would go toward the development of one of those. And when you really get fancy, you can take things like surrogate modeling that lives on neural networks, take that information back, take information you've got in a cloud somewhere, connect that to an edge device, and get real-time insights and even control into the process itself. So when you're dealing with something like safety, where pressures can change quickly inside a reactor vessel or things like that, these digital twins, I actually foresee being probably an imperative in the future in terms of deployment of these kinds of assets from a power generation perspective. So, or even a steam generation perspective. So this is not tomorrow's stuff for us. These are things we're doing right now. And as you encounter those needs, I would encourage you to reach out and let us kind of help you down this path. We've got a lot of capabilities internally. ATA has a lot of PhDs, as Adam mentioned. There's not too many disciplines you're going to encounter that we can't help you come up with some kind of solution for. So as you go down this path, feel free to reach out. This is something that I think, again, is going to become very important in this space. If it's not, you guys, those of you on the call may already be going down this path. I know a few that already are. So we got all this simulation data, we got all this information. We may have hundreds of simulations of simulations. We have an issue eventually, like any other large store of information, you wind up with a documentation control issue. And when you're dealing with something as complex as what you guys are designing, you're going to have some way to manage revisions, to manage history, and to understand how any changes you may make to a single element in your design process relates back and affects other things. So we have a solution for that called TC Sim. And if you're using Teamcenter already, it makes a lot of sense. So this is something that we have, I don't think we do a good enough job of talking about, but it's a really, really handy tool for this. And it mounts, as I mentioned, right up to Teamcenter. It allows you to do like manual workflows, semi-automated workflows, and fully automated workflows too. And and one of the interesting things about HEADS is it gives you a place to put this data so you can link these things together, and you can do like multi-disciplinary optimization using HEADS. So you're not just optimizing necessarily just the star content, you're optimizing a spreadsheet with Flowmaster or your flow calculation software with your thermal and fluids and heat transfer models. So you can do all of it in one place, and you can still use those same tools to optimize it, and it just makes it easier on everybody. So there's some really interesting content I reviewed a couple of days ago online, but if you're interested in TC Sim, I'd go check it out. I think it's really a compelling case when you're dealing with a lot of engineers working on a complex project like this. So with that, I think I'm going to let Mr. Thornton come in and talk a little bit about taking these concepts that I just presented to you guys and really taking it deeper. Model-based system engineering is something that in the last 6 months has really taken off, especially in the nuclear space. And I really appreciate Brian taking the time today to present this to you, and I think it will resonate.
Thank you very much. Just for your background, my name is Brian Thornton. I'm with Siemens, and I'm a member of our portfolio development organization. And my sole function within the company is that of model-based systems engineering. And what I do is I help customers assess, plan, and initiate their model-based systems engineering business transformations. So what I'd like to talk to you about for a few minutes is turning complexity into a competitive advantage through model-based systems engineering. There's a lot of confusion in industry, heck, even amongst my colleagues, what model-based systems engineering is. So I like to begin these discussions with this definition that I borrowed from the International Council on Systems Engineering. They crafted this definition back in 2020, and it's easily understood. And just briefly, I'd like to share this with you to level set what I mean, what Siemens means by MBSE. And at its simplest form, it's the formalized application of modeling to support system requirements, design, analysis, verification, and validation activities beginning early upfront in that conceptual design phase, and then continuing through product design, verification, and validation, into manufacturing, and ultimately into sustainment of that product. So MBSE is a very, very broad topic. What I will focus on today is what Sean has been talking to you about, and that is design, verification, and validation. So why has model-based systems engineering become necessary? In large part, it's because designs have become more and more complex. The products that we're taking to market today are smarter, they're more deeply connected across systems than ever before. In effect, what we're developing and selling are a system comprised of multiple systems. And as a result of that, what used to be a very well understood responsibility within an engineering enterprise, those responsibilities have become blurred. You know, when I graduated as a mechanical engineer, my domain was fairly well understood, but with the integration of mechanical, electrical, electronics, and networks, it's now about the integration across these domains that enable us to deliver against performance requirements. And as such, the way we've been approaching this in the past is no longer sufficient. We can't operate as siloed teams that are responsible for, say, the mechanical aspects of a product or the electrical aspects. It's about integration, as I mentioned previously, and it's about digitally linking these activities together such that we can overcome this complexity and literally turn this complexity into a competitive advantage. And that's what I'm going to focus my discussion on this afternoon. So this is an interesting insight that we've gleaned in speaking to numerous customers across different industries. And that is between 30 and 70% of program schedule time is consumed by integration issues. And as this plot depicts here, most of these integration issues are surfaced after initial prototypes become available. And this is where we begin to dive into heroic integration across electronics, software, electrical, mechanical, and networks to remedy these problems. And as you can appreciate, when we're this deep into the product development process, the cost of implementing a change has gone way up, and our flexibility in terms of what we can implement has gone down dramatically. So what we're focused on is making a dramatic shift to the left, where we perform continuous integration across these domains, and we digitally verify our performance using technologies like Sean has shared with you. And we enable this by facilitating a significant flow of information through what we call a digital thread that literally pushes the information to an analyst such that he or she has what they need at their disposal to go about their creation of their digital twin, executing that model, and then comparing predictive results to their requirements and determining whether their design is sufficient or if it needs additional rework. So when I meet with our customers and talk about model-based systems engineering, you know, this represents what we typically see. And that is, we typically find air gaps that exist between organizations, users, and tools. And I like this phrase, going out on a data safari. You know, whenever we undertake a verification or validation of our product, we need information to do that. A very interesting internal benchmark was performed by Rolls-Royce Aerospace, and they determined that 30% of their analyst time is spent either seeking or providing information. Another interesting aside is the same study revealed that 32% of the analyst time was spent in meetings. So that effectively left about a third of their time to create models, run them, produce results, and iterate. And that's just far too little time. So it's about pushing information to these stakeholders so that they have sufficient time available to go about their verification and validation activities digitally before we're manufacturing those very costly physical prototypes. We also see that teams frequently work independent of each other, which makes digital and physical integration a challenge. And last, that design changes that are made by one stakeholder in an engineering enterprise often goes unknown by impacted stakeholders until formal design reviews are performed, or worse. And the or worse is we're already manufacturing prototypes and we're flying it, we're taking it out to the lab, we're driving it, we're firing up that plant, and then we find we've got some significant issues that need to be resolved. A good example that I have here that talks about the impact of being integrated from the onset of your product development activity lies in this example here with Boeing commercial aircraft. They experienced a dramatic improvement in their business process on the 787 program. But before I share the success, I want to talk to you about the motivation for that business process change. And the motivation lied in the 777 aircraft. What you see here in this white box is a list of subsystems that comprise a Boeing commercial airliner. And what's interesting to note here is when you consider all the interactions taking place across these subsystems, in Boeing's case, it numbered 1.2 million interactions. So it's a very complex product, as you can appreciate. And in an attempt to manage all these interactions across all of these subsystems, Boeing utilized a paper-based process called interface control documents, or ICDs. ICDs are still commonly used throughout industry today, and it's a good means to understand what's being impacted by what when there's a design change made. But when we're talking about 1.2 million interactions, and we have over 100 engineers that are solely focused on maintaining and keeping these ICDs up to date, it takes an awful lot of work, and it's never in real time because it's a paper-based process. Anyways, fast forward to the maiden flight of the 777 aircraft. Boeing engineers documented just over 16,000 interface issues across all of these subsystems. This had a very profound impact on Boeing's financial reporting. If you take a look at, well, before I talk about the financial impact, it took 18 months for Boeing to clear all these interface issues such that they were then capable to begin delivering aircraft to their customers. So over the course of 18 months, when they began delivering aircraft, Boeing delivered 200 units to their customers at an average sale price of $260 million per airliner. And if you multiply those together, that equals about $52 billion worth of revenue that was deferred for 18 months because they couldn't ship aircraft until all of these issues were resolved. This was the motivation for the business process change on the Boeing 787 program. They brought in a new chief systems engineer. His name is Mike Sinnott. And what he did is two primary things. One, he introduced Siemens technologies that enabled them to model the logical interfaces across all of these subsystems, such that when a design change was made in one of the subsystems, let's just say it's flight controls in the first bullet there, the flight control electronics, everything that flight controls electronic subsystem interfaced with was understood. They could map who was impacted by that design change. And then Mike Sinnott implemented the secondary change, which was a business process change, where he required his engineers to physically sign off that he or she could still meet their local performance requirements in light of this design change that happened elsewhere in the engineering enterprise. And this had a profound impact on Boeing's ability to produce a first-time capable aircraft. When they flew the very first 787, they documented 0 interface issues. So in one commercial aircraft cycle, Boeing went from over 16,000 interface issues on the 777 aircraft to 0 interface issues on the 787. And this is it's a great example. It's one of the few customer examples that we can publicly share, but it really shows the value of digitally connecting your enterprise and being able to assess the impact of design changes in real time so that you actually have time to take corrective actions and iterate on your designs to maintain continuous compliance with your requirements. So let's talk about how Siemens helps its customers turn complexity into that competitive advantage. Sean spoke to you about Accelerator. And Accelerator is our integrated portfolio of software services and application development. And it really is comprised of 3 key enablers from a model-based systems engineering perspective. The first is the provision of an end-to-end product lifecycle and a continuous digital thread that spans from that upfront conceptual design through verification and validation of your design, through manufacturing and ultimately sustainment of your product, and looping that back to subsequent programs. The second key element is the provision of our comprehensive set of digital twins and design exploration capabilities. Sean peeled that back for you so you have a greater view into the solution sets that are available through our Accelerator portfolio. And then last, and very, very importantly, is Accelerator is flexible and it's open. Siemens understands that our customers are not going to holistically standardize on our entire software portfolio. So it's important that we enable our customers to carry forward investments that they've made in certain technologies because frankly, they deliver a lot of value. You've built methods and processes around these investments. It's important for us to do that. So we adopt and maintain adherence to standards. We've created linkages to third-party, commercial tools such that we can carry these investments forward and enable them to participate in the product life cycle and bring more value through model-based systems engineering. So if we look at our platform for model-based systems engineering, you see our tagline up there, get connected, stay connected. I know this looks like a little bit of an eye chart, but what I'm going to do is walk through this very briefly from a workflow perspective and talk about key concepts, key capabilities in each one of these phases of the verification and validation of our products so that you can understand how Siemens brings value to our customers and how we start initiating model-based systems engineering. So let's begin with concept design. In concept design, as we talked about before, these products are more and more complex than ever before, and they really benefit from having a numerical approach to identify the best possible product architecture to deliver requirements. To facilitate this, Siemens has developed a patented web-enabled application that replaces what I'll call guesstimation with numerical calculation. And what this does is it enables our customers to evaluate tens, hundreds, even thousands of potential candidate architectural solutions to ID the very best product architecture to deliver multi-domain requirements for given constraints. And this does a couple of very important things for our customers. One is it provides a qualified foundation for performing conceptual system simulation. That's the very upfront beginning upper left-hand side of the V. And the second thing that it does is it enables our customers to take that architecture and develop with confidence detailed architectures across all product domains, such that that serves as that digital blueprint for creating digital twins and verifying performance downstream. As we move into product definition, this is where we begin to synthesize and formalize our requirements. We begin to create formalized and detailed system models across mechanical, electrical, electronic, software, and network domains. And by definition, this would be a multi-domain architecture. So these multi-domain system architecture models provide an interface blueprint. I like to think of it as like an actual blueprint to guide the construction and integration and verification of your product. So Siemens' solution here helps guide the users in the creation of these system model architectures. Other commercial solutions have no methodology associated with it. So you can imagine there's a lot, it creates a lot of variability in the work products that are being produced. Second, the models that are created within our system modeling solution are easily decomposed into shareable subsystems and components which span all product and engineering domains. And again, Siemens has the ability now through our digital thread to share these appropriate system models and distribute them, push them literally to the right individuals in your engineering enterprise at the right time so that they have what they need to go about their development task. We can all appreciate that, you know, we've got very aggressive schedules, and that in order to maintain these schedules, the timely delivery of information is critical. What I mean by that is, you know, Sean was talking about, you know, going off and performing your simulations. Well, to do that effectively, we need to have requirements. What are we going to measure our predictive performance against? What are the test cases we're going to exercise those models against to verify our performance against those requirements? Ideally, we should be working from an architecture such that the work product, the model, a digital twin that's created in one department is compatible with the model that's created in a completely different department. If we don't follow an architectural construct, these models are not easily connected and integrated. We all need parameters to support our modeling activities. You know, today we have to go out on a data safari to try and find engineering parameters to populate our digital twin models and go off and perform our simulations. And in some instances, like computational fluid dynamics, maybe a structural consideration, we may need some 3D geometry to go about creating our models. It's the compilation of these 5 items that we call a verification package. And again, utilizing that digital thread that we have available within Teamcenter, we're able to push that verification package to the appropriate individuals within the engineering enterprise such that they can go about their assigned tasks. And this goes a long ways towards bringing an end to that data safari that I spoke about a few minutes ago. Rather than going out and hunting for information, we're literally able to collate the information and push the information to the end users so that they have what they need to go about their simulation activity. I'm going to skip this particular example just for time's sake and move into what do we do with these requirements? What do we do when we receive that verification package and that architecture? With the verification package in hand, your resources now have what they need to create their digital twin and perform their assigned verification. As I cited before, that system model, it serves as a blueprint that guides the creation of digital twins across all product domains. And then your engineers in the mechanical, electrical, software, electronics, and networks areas can exercise their models at the local level to assess their performance against their assigned requirements. And then they iterate as needed until they're capable of meeting their local requirements. And, you know, local performance is while it's important, it's about the integration of all these contributions that yields a product that meets overall product level performance requirements. And that's why this digital blueprint is so important. It enables digital twins, these CAE models from one organization, to be compatible with those from another. And that enables us to digitally integrate these models much earlier in the product development process than we ever could previously. And then, as I spoke about, we talked about, you know, local verification, but really, you know, it's a good start. It's about balancing performance across all product domains to produce a well-integrated solution. And Siemens enables its customers to perform multi-attribute, multi-domain design space exploration such that you can balance performance across product domains and across product level requirements. And any resulting design changes, those updates are pushed to people that are impacted by that change. So reflect back on that Boeing example. You know, when a design engineer made a change to the flight control electronics, everybody that was impacted by that design change received this type of notification, and he or she could verify if they could still meet their local requirements or not. And if they couldn't, they would update their design, and then their design change would be pushed to people that are impacted by that. And this is what enables that continuous performance verification and validation across the enterprise. This is when model-based systems engineering really begins to deliver its maximum value. So in summary, Siemens helps its customers bridge, orchestrate, and accelerate the product development process. We do that by helping our customers identify the best possible product architecture by enabling them to numerically evaluate candidate architectures to find the best solution. We help drive simulation by pushing the right information to the right person at the right time, such that they have at their disposal what they need to create their models, execute their models, and measure their predicted performance against requirements. We enable our customers to virtually integrate earlier in the product development process by utilizing these simulation architectures that guide the construction and integration of your digital twins. And in doing so, we've gained some time. At this point, we actually have the opportunity to begin balancing performance by performing multidiscipline design exploration that helps you meet all performance requirements, not just local performance requirements. And then at this state of maturity, we enable our customers to continuously verify and validate. You'll be able to see what's changing and verify that requirements are met with these up-to-date design changes. And last but not least, all of this brings with it a very, very high degree of confidence. Siemens Continuous Digital Thread links the results from these predictive models to everything that produced them. So we know what parameters were used. We know what revision of geometry was applied. We know what requirements were linked to the test cases that we're measuring our performance against. Everything is auditable. And in the nuclear power generation industry, auditability of your processes is critical. So just a brief summary here of a couple of recent announcements, joint announcements with our customers, where they announced their partnership with Siemens and their adoption of Accelerator. The first example here was with Hyundai Kia. Hyundai Kia made a dramatic transformation in terms of their product lifecycle management solution. They transitioned to Teamcenter after utilizing their incumbent solution for just about 30 years. They determined that the platform that they were on was not capable of delivering them to their desired end state. So they are transitioning from their incumbent solution to Teamcenter. And in the same process, they also are migrating their design solution from a competitive solution to NX. Another important announcement was issued by Siemens and Northrop Grumman. Northrop announced their adoption of Accelerator to complement their initiatives to harness digital technologies across the product lifecycle. And last but not least was a recent announcement with Lockheed Martin, where they announced their partnership and adoption of Accelerator to transform their product development process. They anticipate that this transformation will compress their product development process by a little over 30%. That concludes my discussion. I appreciate your attention and your time, and please make note of my contact information if you have any questions or would like to have follow-up dialogue regarding model-based systems engineering. Thank you very much.
Thank you.
Excellent. Thank you, Brian. That was great. So Sean, I think the question was, can HEEDS integrate other tools aside from Siemens? Can you give us a few thoughts on that?
Yes, I can. So these are some of the portals we have. It's not an exhaustive list, but you see, SolidWorks, yes. That's out of the box. So you can also do Excel. You can also write custom scripts to import data as well. It's done all the time. It's very open. It's very open, and it's very easy to integrate these things and create these templates that allow you to automate those workflows. So yes, we can.
Excellent.
Yeah, and I'll jump in. This is Jonathan. So I have two that I think came to me, but if you're out there and have additional questions, I invite you to put those in the chat, or if you want to request to unmute yourself, put that in the chat too. My first one is for, actually they might both be for Brian, or one of the Brians, I guess. If AIMSIM can model basic elements of a compact reactor system and its accessories, how do you account for the unique elements of new reactor designs, which necessarily are not part of the AIMSIM model library? Brian Thornton, that might be one for you, maybe?
I've got some familiarity with AIM-Sim. So specifically, you're talking about the element that you're interested in creating a 1D model of is not available in the existing library, correct? Is that the question? And then the follow-on question is, how do we accommodate that? Did I understand that correctly?
Yeah, I think that's the intent.
Okay, if you have your own unique physics that you wish to use within AIM-Sim, we have the ability to capture those physics and make your own proprietary element within AIM-Sim such that it can be reused across the engineering enterprise over and over and over again. So AIM-Sim offers a high degree of flexibility in terms of the physics that you wish to implement or use within the AIM-Sim environment. You're not limited to off the shelf, out of the box libraries and elements that we deliver. Did I answer your question? I'm sorry.
Yeah, I think that does it. And I have kind of a similar, maybe more broad, I guess, just multi-body or system simulation in general, just for a comparatively, small new nuclear startup or really an Indian industry. How would those sorts of startups, those small companies, get started early with MBSE and maintain its usage throughout the product lifecycle?
Yeah, it's a great question. I'll submit that just based on the customers that we've been engaging with on the model-based systems engineering topic and journey, those that are, how do I say this? Those that are not burdened with a rich legacy of simulation, design processes, it's easier for them to adopt because there's less complications. Let me put it that way. When it comes to implementing model-based systems engineering, it's a very complex topic. As I mentioned before, some of our customers desire to carry forward previous investments, and that absolutely can be done, and we do that with regular frequency. But the customers that we find that are adopting it easiest are the ones that are, startups that don't have, a rich history of implemented solutions. And in terms of how do you go about it, there is a logical sequence to implementing model-based systems engineering. The first principal step is to identify and manage and apply your requirements. Everything that you do should relate back to requirements. Requirements will determine when you've succeeded or you haven't. And it's really important that we have an effective managed requirements solution in hand, and then we begin to progress from there. A secondary step that makes a lot of sense for our customers, and again, I'm not trying to prescribe, this one size fits all, because every customer is unique. But a secondary step after requirements are managed is to begin authoring these digital blueprints, these system models, because that construct will aid tremendously when it comes to integrating your CAE assets together such that you can move from a local domain consideration to a subsystem and ultimately to a system level simulation. Without that architecture, integrating models becomes very, very challenging. I didn't get a chance to introduce myself at the beginning, but prior to this role, I was the account executive for Ford Motor Company. And one of the biggest challenges that Ford has is integrating the work product from different departments together such that they can gain a view into system level performance early in the product development process. Ford can simulate virtually anything they need to simulate with physics, with the tools that exist in the industry today. But where they're really challenged is taking a model from, say, the electric motor department and linking that up to a model from the battery department and linking that up with a model of an inverter such that you've got an electric powertrain system that you can now virtually test drive and evaluate at the system level. So, steps are requirements, architectural modeling, so that you've got a blueprint of what you need to go off to, and create, and how you can link those assets together to gain a view into system level performance would be a couple of prime areas to focus.
Brian, that's excellent. Thank you. Can I add to that too? In that, from a business perspective, and if we're talking about new startups wanting to follow this practice, Siemens offer a lot of startup packages. One that includes many of the components that I think are needed to start a model-based systems approach. So Teamcenter, AIM-SimStar, NX, all the basics to get a startup rolling on this journey are in the simulation for startups package that is very attractive. So that's a thought to think about too.
Perfect. Thank you, Adam, Brian Haley, Brian Thornton, Sean. Just thank you all. I don't see any other questions in the chat, so I will just note that we were recording today. We'll get that recording up hopefully in the next day or two. Anyone who registered will get a notification when that happens. And otherwise, Adam, I'll turn it over to you to wrap up.
Excellent. Well, I think we're in good shape. I think you wrapped up very well, Jonathan. Thank you, everybody, for attending. We look forward to talking to anyone who's got questions after today. Thanks again. We'll close the meeting. Have a good afternoon.
Thank you.